We are now going to look at Lewis structures, which is the way that we will represent simple molecules. So a Lewis structure is just a drawing that shows the covalent bonds and the atoms themselves. And we can represent the electrons in a couple different ways, but for right now we're going to represent them as dots. Now we're always going to be interested in the electrons in pairs, not as single electrons for this process. So we're always going to see them together in some way or another. The electrons can be shared between two atoms, and we would call that a bonding pair of electrons or a shared pair. So let me look at these structures that we have here, and I would like to highlight, first of all, the shared or bonding pairs. Here's a hydrogen atom and here's a hydrogen atom, and right here this pair of electrons is shared between those two hydrogens. Now remember, hydrogen only wants to have a duet. It doesn't need to have an octet. So the hydrogen atom on the left thinks it has 2 electrons, and the hydrogen on the right also thinks it has 2 electrons. Apparently it also thinks it has a piece of that H, but it doesn't. And these electrons are shared, so these hydrogens are both somewhat stable. They are satisfying the duet rule. Now let's take a look at chlorine over here. Chlorine has a pair in between the two chlorine atoms. So the chlorine molecule is sharing that pair right there. Now you notice there are many, many more dots there, and those dots stand for the lone pairs. So let me indicate those. So this chlorine atom on the left here thinks it has these pairs to itself, and these pairs to itself, and these pairs to itself. And then this chlorine on the right, and then this chlorine atom here thinks it has that pair, and that pair, and this pair here to itself. Now chlorine would like to have an octet. So we can see that each chlorine has an octet. It's surrounded by 8 electrons, even if some of those electrons are shared. So the chlorine on the left has 2, 4, 6, 8 electrons, and the chlorine on the right, I know I've kind of covered up the electrons there with that dark color, but they're still there. This chlorine on the right also has 8 electrons, so we say it also has an octet. Remember, the goal is to get the same electron configuration as a noble gas, as it were. That was why we wanted 8 electrons. And so this satisfies both of these molecules. So we want to get to an octet for all atoms other than hydrogen, which want a duet. And sometimes it's not possible to do that just by sharing single pairs of electrons between atoms. So it is possible to share 1 pair, 2 pairs, or 3 pairs between nonmetal atoms. If we share 1 pair of electrons, we get a single bond. Sharing 2 pairs gives us a double bond, and sharing 3 pairs gives us a triple bond. There are no quadruple bonds or anything higher when we look at the bonds between nonmetals, like we do in this chapter. So here we can take a look at some examples of double bonds and triple bonds. So if we look at this carbon and oxygen, we see that there are 2 pairs in between them. And so we can say that here's a pair and here's a pair. And so since there are 2 pairs of electrons between the atoms, that is a double bond. Here we have a nitrogen with another nitrogen sharing 3 pairs. So here's a pair, and here's a pair, and here's another pair of electrons in between them. So that would be considered a triple bond. Between this carbon and this hydrogen, we have a shared pair. And between this carbon and this hydrogen, we have a shared pair. So those are single bonds because there's only a single pair between them. And then finally, This oxygen has this pair of electrons and this pair of electrons to itself. We call those lone pairs. And this nitrogen has this pair to itself, and this one has this pair to itself. So let's take a look then at how each atom has achieved its octet. So the carbon needs 8 electrons around it. It has here 8 electrons. 2, 4, 6, 8. This oxygen has 2, 4 from its lone pairs, and then 6, 8 from the carbon, so it has an octet. Now hydrogens can only make single bonds. Remember, they want a duet. It's a very important rule to note, and I would be sure to write that down. So hydrogen here is content because it has 2 electrons, even though those are shared. And the same is true with this hydrogen here. It's satisfying its duet rule. So all of these atoms are happy in the language of Lewis structures. How about this nitrogen? It wants 8 electrons, so it's got 2, 4, 6 electrons from the triple bond, and then 2 more for 8 from its lone pair. So the nitrogen on the left has an octet, and then this nitrogen has 2, 4, 6, 8 electrons as well. So it has an octet. Now, you might be noticing that all these dots can really give you a headache after a while. So what we're going to do now is we're going to say, we'll keep the dots that are lone pairs, but let's replace the shared pairs with lines instead. So for example, between this carbon and this oxygen, instead of putting 2 pairs of dots, let's put 2 straight lines. Between this carbon and this hydrogen, let's put a line, and this carbon and this hydrogen, a line. And between this nitrogen and this nitrogen, instead of 3 pairs of dots, let's put 3 lines. And so this is what we get in those circumstances. So here is the nitrogen molecule we just looked at. It has a triple bond, represented by these 3 lines. Much easier to draw, much clearer. And then these dots are still lone pairs. Here is the molecule involving carbon, oxygen, and hydrogen I just showed you. This is called formaldehyde. And so we have here a double bond, and then these are single bonds. Notice also how I've drawn these as far away from each other as I can in 120-degree angles. There's going to be a reason for that that we'll see shortly. And then here we have hydrogen with a single bond. Remember, hydrogens can only engage in single bonds. And here we see chlorine making a single bond between the 2 atoms, and each chlorine has 3 lone pairs. Make sure that for every atom other than hydrogen, you can see how each atom is meeting an octet rule. Let's go through it one more time. So this chlorine has 2, 4, 6, 8 electrons. This nitrogen has 2, 4, 6, 8 electrons. I could do the same for this nitrogen, 2, 4, 6, 8. Carbon has 2, 4, 6, 8. The oxygen has 2, 4, 6, 8, noting that the bonding pairs are double counted between the 2 atoms. So now we'd like to know how to draw the Lewis structures on our own. There are several steps, and I need to emphasize this point very strongly. When we are drawing Lewis structures, you must follow the steps I give you in order. If you skip around or try to do it yourself, you're almost certainly going to make a mistake. And this can be a critical error on an exam, because making a mistake on the Lewis structure will then cause mistakes on any of the follow-up questions. So it is critical that you go through these in order. So if there's a rule 0, that's rule 0. Follow the rules. Now that said, in my 5 steps, step 1 and step 2 could go in either order. But other than that, everything else must go in order. So be sure to write these in your notes. You should be taking plentiful notes as you're watching these videos. So step 1. You want to look at the formula of whatever it is you're going to draw the Lewis structure for, and you want to get the total number of valence electrons from those atoms. So nitrogen, if you look on the periodic table, is in group 5A. So it has 5 valence electrons. So I put a 5 there. And there's only one of them. So 5 times 1 is 5. Hydrogen is in group 1A, so it has 1 valence electron. But there are 3 of them. So we need 3 times 1, which I put over here. So 5 plus 3 times 1 is 5 plus 3 is 8. So there are 8 valence electrons in ammonia, NH3. Notice I'm not counting any of nitrogen's electrons that are not valence electrons, so only valence electrons. As an aside, I would note that if we're doing a polyatomic ion, that any positive charge means we have to subtract an electron, and any negative charges mean we add electrons. So for example, if this was NH4 plus, it would have been 5 plus 4, because we would have 4 hydrogens, and then if there's a plus charge, you subtract 1, because remember, positive charges mean you've lost electrons, and that would still have 8 valence electrons. For now, I just want to focus on molecules which do not have any charges. Step 2, and again, step 1 and 2 can be interchanged. And step 2 is probably the trickiest of the steps. You want to draw a very simple, what I would call skeleton of the molecule, and we want to show which atoms are connected to which. The molecules I want to focus on right now all have exactly one central atom. And the definition of central atom is any atom which is bonded to 2 or more different atoms. So there has to be 2, 3, or 4 atoms on the side of a central atom. And when trying to figure out which atom is the central atom, it's usually the least electronegative one. That's why we wanted those electronegativity values. Hydrogen can only make one bond, so therefore hydrogen can never be a central atom. So you'll never put hydrogen in the middle of the molecule, even if it's the least electronegative. It doesn't matter. Hydrogen can't be central. So in NH3, since hydrogen cannot be central, the only atom which could be central is nitrogen. So we'll put it in the middle, and then we will draw bonds to all the other hydrogens. Notice I did not go nitrogen to hydrogen, hydrogen to hydrogen, hydrogen to hydrogen. That would have been wrong. So the way the formulas are written, NH3, it's always assumed that all the atoms that come after the nitrogen belong to that nitrogen. Now we have to do some math, or accounting. We want to figure out how many electrons we have left that have not been accounted for. So every bond that we drew counts as having 2 electrons. So looking at the structure here, we've drawn 2, 4, 6 electrons so far. In step 1, we said we have 8. So 8 minus 6 means we have 2 electrons left to put into the structure. Step 4. You want to give electron pairs to each atom so that each atom can get an octet. Okay? Hydrogen will never get a lone pair, so we don't have to worry about that. So that's another very important thing. Hydrogen makes one bond and never has lone pairs. So electron pairs go to the most electronegative atoms first. They are the greediest for electrons. So that means they're going to go on the central atom last. Very important. You must stop adding electron pairs when you run out of electrons. Remember that right now, in our drawing of ammonia, we just had 8 minus 6, which would be 2 electrons left, and I can't add more than 2 electrons to my structure. So here's what we had before, and then I noticed that the nitrogen had 2, 4, 6 electrons. It needs 8, So I put those 2 electrons on top as a lone pair. 2 minus 2, 0. I have no electrons left. So now what we do is we check to make sure everything is happy. Hydrogens each have a bond, they're happy. Nitrogen has 2, 4, 6, 8 electrons. It's happy. We're out of electrons. We're done. This is the Lewis structure for ammonia. Now note, you could have drawn it a little bit differently. You could have put the hydrogen up here and the lone pair on this side instead, or you could have put the lone pair on the bottom and the hydrogen on top instead. That's all fine. The one things that you do not want to do is you don't want to ever draw the lone pairs and the lines right on top of each other, because those are difficult to read, and you always want the lone pair dots to be extremely, extremely clear. Now you also want to do this only with pencil because of the next rule. This step is not always necessary, and as we just saw a moment ago, it was not necessary for ammonia. Let's say you have run out of electrons, and we still need to get an octet on some atoms. How are we going to handle that? Well, what we do is we go next door to any atom which has a lone pair, and we beg for electrons from that. So we say to that atom, I want you to change that lone pair into a double bond between me and you. And that's exactly what it will do. It will change that lone pair to a double bond. Oftentimes, that fixes the situation, and now the central atom has an octet and everything's fine. If that's not the case, then you either make that same atom share another lone pair, if it has it, or if there's another atom next door with a lone pair, you make it share 2. So you can borrow from 2 different neighbors, or just borrow twice from the same neighbor. Fluorine is the most electronegative atom. It is ultra greedy, and it will not share its lone pairs. So it won't do that. I would like to do another example with carbon dioxide so that we can see Rule 5 in action. Okay, so let's take a look here at carbon dioxide. So here's our formula. So step 1 is we're going to count up the electrons. So carbon is in group 4A, so it has 4 valence electrons. And oxygen is in group 6A, so it has 6, but there's 2 of them. So we're going to have here 4 plus 6 times 2, which would give us a total of 16 valence electrons. 16 valence electrons. After a while, you can just do this in your head, but you always want to double check. All right, now we want to draw a simple skeleton. The carbon is probably going to be it. It's usually the element that comes first, except not hydrogen. So we ask ourselves, what's more electronegative, carbon or oxygen? Oxygen is more electronegative. That means carbon will be the central atom. So I'm going to draw here a carbon. And if I've got 2 oxygens, you always want to start by drawing them as far away from each other as you can, so at total opposites. Okay, and that last one's a little ugly. And it's not much better, but I'll stay with it. All right, so let's see where we're at right now. So we have 16 electrons. Now we subtract 2 for every bond we've drawn. So we are going to subtract 4, and we're down to 12 electrons. Now what we need to do is give lone pairs to the most electronegative atoms, which would be oxygen. So we've got 12 that we can do. The oxygen right now has only 2. Remember, it wants to get to 8. So we've got 2, 4, 6, 8. So I just drew in 6 electrons. So I have 6 left. I'm going to do the same thing with this oxygen here. And I have 6. And so now I'm out of electrons. The oxygen has an octet, the oxygen has an octet. The carbon, however, does not. So what are we going to do? Well, in this kind of a circumstance, we go to step 5. We go begging to the neighbors. So we can come to either one of these oxygens and say, can you turn that lone pair into a bond between me and you? And that's what it's going to do. So let's get rid of that lone pair. And we will change it into a double bond. Carbon has 2, 4, 6 electrons. Still not an octet. At this point, you're actually given a few choices. You could borrow again from the same oxygen, and that would give an acceptable answer, or you could borrow from the other oxygen. And at this point, I want you to generally favor being symmetrical in that kind of situation. So if you did it from the left, do it from the right. Usually you'll want to borrow from the less electronegative atom, but since these are both oxygens, you didn't have a choice. All right, so some things to check. Is CO2 the formula? COO, yes. So we have the right formula. We have our count here of 16 electrons. Let's make sure that this works. So we've got 2, 4, 6, 8, 10, 12, 14, 16. So we've got all 16 electrons accounted for, none over the limit and none below the limit. And finally, does every atom have an octet? Oxygen has 2, 4, 6, 8. Carbon thinks it has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. So this is a valid Lewis structure for carbon dioxide. So now I'm going to give you several examples to practice with. So I would like you to pause the video and try drawing Lewis structures for each of these molecules. You might want to go ahead and pause them and do them one by one. So I will go through them one by one in order. And that way, after you've seen one of these molecules, you can proceed to the next one and see if you've made any mistakes, and hopefully you resolve mistakes before you get to the more difficult molecules. So go ahead, pause the video, and when you've done at least CH4, you can go ahead and continue the video. Okay, so let's go ahead and start off with methane, CH4. We'll start by doing the electron count. Carbon has 4 valence electrons because it's in group 4A. Hydrogen, as we know, has 1, and there are 4 hydrogens there. So each one of them supplies 1 valence electron for a total of 8. We'll start with our skeleton here. So we put carbon in the center. And then we're going to attach the 4 hydrogens. And let's see if we can make this one a little nicer over here. Much better. And now we want to see how many electrons we've taken into account. So we've got 2, 4, 6, 8. So of my 8, I'm down to 0. That's very unusual. We need to make sure that every atom has an octet. Carbon does. 2, 4, 6, 8. Each hydrogen has 2. There's really nothing else we can do. So this is the correct Lewis structure for CH4. Water. Hydrogen has 1 valence electron, and we have 2 of them. And we have 1 oxygen. So again, we have 8 electrons. Hydrogen cannot be the central atom, so oxygen has to be in the center. And I'm going to go ahead here and attach my two hydrogens. Notice that I'm initially drawing them as far away from each other as I can. So we had 8 electrons. I've now included 4 of them already, so we need 4 more electrons. Well, the oxygen here only has 4 electrons. It needs 6, 8. And we are now down to 0. And we notice all the atoms have octets that need 2, really only oxygen, and the hydrogens are here. This structure is fine, but for reasons that will come up a little bit later in the chapter, I would strongly advise you to do the following. Whenever the central atom has lone pairs, these are never going to really be straight. This is what's called a linear shape, and that's not going to be the case. So I would recommend redrawing this like this. And as I said, I'll explain why a little bit later. You'll notice it still has the same number of electrons, but it's going to turn out that this is a much better representation of water than this is. Remember, we only want to angle things if there is at least one lone pair on the central atom. Other than that, keep them straight. The next molecule is hydrogen cyanide. Here we have 3 different atoms. So hydrogen has 1 valence electron. Carbon is in group 4A, 4, and nitrogen is in group 5A, 5, for a total of 10 valence electrons, something a little different. Okay, let's find the central atom. It's probably going to be the one in the middle here, but let's make sure that's the case. So hydrogen can't be the central atom. The least electronegative between carbon and nitrogen is carbon. So carbon is most likely the central atom. It certainly is in this case. And it is bonded to hydrogen and nitrogen. Let's look at our electrons so far. So we had 10 electrons to start with. We've drawn in 2, 4. So we're down to 6. So who gets lone pairs? Hydrogen never wants lone pairs. Nitrogen here only has 2 electrons, so let's give it 2, 4, 6. And now nitrogen has an octet, and we are out of electrons. Uh-oh. Carbon doesn't have an octet. 2, 4, it needs another couple pairs. So to get the next couple pairs, what we're going to do is we're going to say, let's get rid of a pair here, and we're going to make that into a bond. And that will bring us to 6 electrons. Let's get rid of another pair. So we're going to put both of those pairs as bonds. And so now carbon has an octet, 2, 4, 6, 8. Nitrogen has an octet, 2, 4, 6, 8. Are there 10 electrons in the structure? 2, 4, 6, 8, 10. Yes, so this is a good molecule. You'll notice I've drawn this one straight because there are no lone pairs on the atom in the middle. Doesn't matter if there's lone pairs over here, just the atom in the middle, no lone pairs. SO2, sulfur dioxide. Sulfur has 6 valence electrons because it's in group 6A. Oxygen is also in group 6A, so we have 6 times 2 because there are 6 of them. So this would be a total of 6 times 3, or 18 valence electrons, quite a bit more. So which is the least electronegative? It's sulfur. So sulfur is going to be in the middle. And for the time being, let's go ahead and draw these bonds straight. and we'll redraw them with angles if there end up being lone pairs on the sulfur. All right, so we had 18 electrons. We are now down to 14 because we've got 2 4 electrons that we have to take into account. So if we've got 14, this oxygen needs 6 more electrons. 2, 4, 6. And this oxygen needs 6 more. 2, 4, 6. And so we're down to 2 electrons. You can't start making double or triple bonds at this point. You still have those 2 electrons. So the only atom that can take them would be sulfur. I'm going to draw them on top. And so now I'm out of electrons. Oxygen has an octet. This oxygen on the right has an octet, but this sulfur has 2, 4, 6 electrons. Well, that's a problem. So what's it going to do? It'll come to either of these next door and beg for electrons. And so let's just take them away from this oxygen. I'm going to take 2 electrons away. And I'm going to make this into a double bond. Now that doesn't look very good. Let's try that again. Quite a bit better. This is, again, technically fine, but it's going to make things harder later. I'm going to redraw this as angled because there is a lone pair on the sulfur, on the atom in the middle. So I'm just going to move this and make sure you keep track of what was there before. So I'll move it down there. Try to make your lines straighter than I just did. And so now, oops, don't do that. We have a more bent shape. And when we get into shapes, this is going to be called bent. We're very creative. Finally, I have phosphorus trifluoride. So let's look at the electrons. Phosphorus is in group 5A, so it's got 5. So you notice you need your periodic table, handy to do this. And now we're going to add a lot of electrons. Fluorine is in group 7A, so it has 7, and there are 3 fluorines. So that means we've got 21 electrons in there, plus 5 is 26. What do you notice about all of these numbers? 8, 8, 10, 18, 26. You should notice that they are all even numbers. And that's going to be required for all of our molecules because electrons have to be divvied up in pairs. We will not encounter any cases of electrons as single dots. They will always be pairs in this class. In reality, there are atoms which have single unpaired electrons, and those are what we call radicals. As the term might imply, they tend to be highly unstable in almost all cases and usually react very quickly to resolve that missing partner. So we're not going to worry about seeing any radicals in this class. We're going to stay nice and stable. All right, fluorine is the most electronegative, so it certainly is not the central atom. Phosphorus is. And so I'm going to start here by drawing these as far away from each other as I can. And so this gives me a, let's see how many electrons. So we have 26. So I'm going to take away 2, 4, 6 electrons. I'm down to 20. Fluorine, being the most electronegative, gets its lone pairs first. So 2, 4, 6, and now this fluorine has an octet, 2, 4, 6, 8. 2, 4, 6, 2, 4, 6. So I've just drawn in 18 electrons, so there are 2 left. And phosphorus doesn't have electrons yet, so 2, 4, 6. We need to give it a pair. And this is an acceptable structure. That said, though, I would urge a change. Just like I recommended that you bend this structure when you have lone pairs on the central atom, I would do the same thing here. And instead of having the fluorine up at the top, I would recommend having it at the bottom, because when we get to shapes and dipoles, it will be much easier to figure out dipoles if they're all pointed in different directions. So you see we still have kind of a bend here. Everything is bent away. All right, so those are the Lewis structures for several different molecules. I'm going to go ahead and stop this video here, and when we come back we will continue by looking at shapes and eventually polarity. Thank you.